You ever sat and wondered, geez, what's the magic that makes my smartphone kinda smarter than me? Just kidding though. But seriously, have you stopped to think about how ridiculously amazing it is that our phones and digital devices can perform tasks with lightning speed and precision? I mean, think about it. Phone trackers can pinpoint your exact location on a map, calculators can crunch complex numbers in a split second, and virtual assistants can understand your voice commands and respond accordingly. It's just like having all your wishes granted just with the snap of a finger. But let's be frank, what really makes this possible? It's the study of computers, computational systems, and the processes that govern their behavior. Imagine trying to understand how a car works without looking under the hood. That's basically what computer science is, understanding the intricacies of computational systems, designing new ones, and making them better. You might wonder why it's called computer science and not just computer studies or something like that. Well, that is because it involves a lot of scientific inquiry, experimentation, and problem solving. It's not just about coding, although for real, coding is pretty cool too. Computer scientists use mathematical and computational principles to study the fundamental nature of computation and information processing. Computer science is like a big umbrella that covers a wide range of cool stuff. There's algorithms and data structures, which are like the secret ingredients in your favorite recipe. Then there's artificial intelligence and machine learning, which are like the superheroes of the computer world. And let's not forget computer networks and cybersecurity, which are like the guardians of the internet. But that's not all. Computer science also encompasses the fascinating world of hardware and architecture. Imagine building a house without knowing what materials to use or how to design it. That's basically what computer hardware components are, the building blocks of computers. Okay, moving on, you've got your CPU, that is Central Processing Unit, which is like the brain of the computer, executing instructions and performing calculations. Then there's the memory, which is referred to as the RAM, and storage, which includes hard drives and the likes that are like the computer's filing cabinets, holding on to data and programs. And let's not forget input and output devices like keyboards, mice, and monitors, which are like the computer's senses, allowing it to interact with the world. Now, moving on to computer architecture. Computer architecture is like the blueprint of the computer. It's the design and organization of the computer's components, determining how they work together to perform tasks. You've got your von Neumann architecture, which is like the classic design, using a single processor to execute instructions. Then there's the Harvard architecture, which is like the sleek modern design, using separate processors for instructions and data. And let's not forget parallel processing, which is like the computer's superpower, allowing it to perform multiple tasks simultaneously. Networking fundamentals are like the roads and highways of the internet. You've got your LAN, that is local area network, connecting devices within a small area, like a neighborhood. Then there's the WAN, that is wide area network, connecting devices over a larger area, like a city. And of course, there's the internet, a global network connecting devices worldwide. Protocols like TCP/IP, that is Transmission Control Protocol, Internet Protocol, and HTTP, that is Hypertext Transfer Protocol, are like traffic rules, ensuring data is transmitted efficiently and reliably. They keep the digital traffic flowing smoothly. But wait a sec. Have you ever wondered how your favorite search engine manages to find that one specific web page you're looking for amongst billions of other websites on the internet? Well, now don't break your back over it. Let's delve into the fascinating world of data structures and algorithms to find out. And to illustrate just how crucial they are, think of a situation where you're trying to find a specific book in a huge library. I tell you, bruh, you could just be searching through the shelves one by one, all day. That could take forever, bruh. And boom, that's where data structures and algorithms come in, like a super efficient librarian who says, take a seat, relax, and I'll find that book for you in a snap. With a few swift keystrokes, the job is done. And voila, the exact book you're looking for appears before your eyes. In simple words, algorithms and data structures are the ultimate library organizers, making quick work of even the most daunting tasks. But what exactly are data structures, and how do they help make this magic happen? Let's take a closer look. Data structures are just like a map that helps you navigate and organize your data. Just as a map provides a clear layout of a territory, a data structure provides a clear layout for your data. You've got different types of data, and you want to store it in a way that makes sense. The goal is to bring order to the chaos, to tame the wild beast that is your data. By using a data structure, you can get your data under control, making it easier to work with and understand. Let's say you want to keep track of your family tree. You could use a data structure like a tree to store all the relationships. It's like a blueprint to your ancestry. With this data structure, you can easily find your great-grandmother's name, or figure out who your second cousin twice removed is. Data structures are essential in computer science because they help us manage large amounts of data efficiently. They're like the secret code that unlocks the full potential of your data. And just like how you need different tools for different jobs, you need different data structures for different problems. There are two types of data structures, primitive and abstract. Primitive data structures are like the basic building blocks of a house. They're the fundamental foundation. Abstract data structures, on the other hand, are like the intricate architectural designs. They're more sophisticated and specialized. Some common examples of abstract data structures include arrays, linked lists, stacks, queues, trees, and graphs. Each of these data structures has its own strengths and weaknesses, and they're used in different situations. It's like having a toolbox full of different gadgets, and all you need to do is to choose the right one for the job. Moving on, let's talk about algorithms. An algorithm is like a set of instructions for solving a puzzle. It's a step-by-step guide that tells your computer exactly what to do with your data. Think of a GPS navigation system. It's an algorithm that tells you how to get from point A to point B. Algorithms are fundamental to computer programming because they provide the instructions for executing tasks. An efficient algorithm can make a huge difference in the performance of a program. It's like the difference between a sports car and a clunky old van. One gets you where you need to go fast, while the other, well, not so much. Some examples of algorithms include finding the fastest route in a GPS navigation system, navigating an airplane or a car, finding what users search for in a search engine, and sorting data. These algorithms are like the conductors of an orchestra. They make sure everything runs smoothly and efficiently. Data structures and algorithms are like two peas in a pod. They're meant to be together. A data structure is not worth much if you can't search through it or manipulate it efficiently using algorithms. It's like having a super fast car without any roads to drive on. It's not going anywhere. Data structures and algorithms are used in virtually every software system, from operating systems to web applications. They're used for managing large amounts of data, scheduling tasks, planning routes, optimizing processes, and solving complex problems. Now, let's delve into the world of computer science theories, shall we? So, you've probably heard somewhere about some random dude automata theory, and you're all, who's that and what's the big deal about, in your head, right? Now let's put it this way. Take for instance, you're trying to build a super smart language detector that can figure out whether someone is speaking Spanish, French, or Mandarin. You definitely need a way to describe those languages, right? Well, good news. Automata theory is the way. The automata theory is just like a blueprint for building language recognizing machines. But here's the thing. Languages are like some crazy complex thing. Plain truth. That's why we need finite automata, regular expressions, and context-free grammars to break them down into manageable chunks. Think of it like trying to assemble a piece of IKEA furniture. You need instructions, diagrams, and a whole lot of patience. Now, let's talk about computability theory. This is like the ultimate reality check for computer scientists. We often assume that computers can solve any problem we throw at them, but that's just not true. Some problems are simply too hard, too complex, or too darn weird for computers to handle. That's where Turing machines come in. They're like the theoretical superheroes of computing, showing us what's possible and what's not. Decidability is another key concept in the computability theory. Think of it like a game of, can I solve this problem? If the answer is yes, then you've got a decidable problem on your hands. But if the answer is no, well, you might need to throw in the towel. On the other hand, we've got reducibility. I will say it's just like a game of problem-solving dominoes, one that says that if you can reduce one problem to another, then you'd know that if the second problem is solvable, the first one is too. It's like a beautiful logical chain reaction. The entire reducibility concept is particularly useful in computer science because it allows us to classify problems based on their complexity. By reducing one problem to another, we can determine whether a problem is solvable, and if so, how difficult it is to solve. This helps researchers and developers identify the most efficient solutions to complex problems. Have you also ever wondered what happens when we try to reduce a problem that's already ridiculously hard? Like trying to solve a Rubik's Cube blindfolded while eating spaghetti? Yeah, it's a real brain twister. Reducibility helps us understand the limits of computation and what's possible, or impossible, to solve. And that's pretty cool if you ask me. And then, we've got some other dude here. Cryptography. It's just like the secret agent world of computer science, all about keeping information safe and secure. Encryption, decryption, digital signatures are just some mouthful of terms that makes cryptography seem like a game of cryptographic cat and mouse. Now, after exploring some of the fascinating concepts in computer science, let's talk about the guardians of the digital world, the ones who keep our information safe from prying eyes. Already thinking about who those guys might be, right? Now, let's take a tour to the realm of artificial intelligence, machine learning, data science, and cloud computing. Don't worry about the bills, I'll foot them. Although there's a condition needed before we start the tour. We've got to set the stage with a brief nod to the security measures that make all these advancements possible. Now that we're done with that, let's kick off. Currently, artificial intelligence and machine learning are making huge waves right now. Here we're talking self-driving cars, personal assistants like Siri and Alexa, and even robots that can do backflips. Seriously, machine learning is a game changer. It's all about developing algorithms that can learn from data, so we can teach machines to recognize objects, navigate roads, and make decisions in real time. And with deep learning, we can tackle even more complex tasks like image recognition, speech recognition, and natural language processing. Now, imagine you're a marketing manager and want to know which social media channels are driving the most sales. You'd need to collect data on website traffic, social media engagement, and sales conversions. Then, you'd use data visualization tools to create interactive dashboards that show you which channels are performing best. Finally, you'd use statistical analysis to identify correlations between social media engagement and sales conversions. That's data science and analytics in a nutshell. More so, have you ever heard of cloud computing and DevOps? It's all about delivering computing resources over the internet, rather than having to manage them on premises. To get a clearer understanding of this, let's take a case scenario of a developer who needs to deploy a new application to a global audience. The developer will have to use cloud infrastructure providers like AWS, that is, Amazon Web Services, or Azure to spin up virtual machines, storage, and databases. Also, the developer will use containerization tools like Docker to package the application and its dependencies into a single container that can be deployed anywhere. Finally, you'd use continuous integration and continuous deployment, CI/CD pipelines, to automate the testing, building, and deployment of your application. It's like magic, but without the top hat and wand. The magic of deploying an application anywhere, anytime. But have you ever wondered how we can make sure that application is not only functional, but also a joy to use? Good news. Human-computer interaction, HCI, is the one that's in charge of that entire field. It is the secret sauce that makes technology usable, accessible, and even enjoyable for humans. Let's start with user experience, which is normally abbreviated as the UX design. To get this, we'll have to go for a very nice example. Let's take, for instance, you're at a restaurant, and the menu is all a mess. Tiny font, confusing categories, and a million options to choose from. You'd probably lose interest and leave, right? That's exactly how it works when the UX design goes wrong. But when it is properly done, UX design is like having a personal concierge who anticipates your needs and makes your experience seamless. The principles of UX design include empathy, which involves the act of understanding the users, consistency, which is the act of using familiar patterns, and feedback, which is the act of feeding the users with recent information and updates. The entire concept is all about creating an intuitive, engaging, and user-friendly experience. Now, let's talk about human-computer interaction, HCI. Here, we'll take a case scenario of you trying to have a conversation with a friend, but unfortunately, they only respond with yes or no answers. Frustrating, right? That's what it's like when computers don't understand human behavior and needs. Human-computer interaction, which is generally abbreviated as HCI, has revolutionized the way we interact with technology. The 1980s saw the dawn of personal computing, with machines like the Apple Macintosh, IBM PC 5150, and Commodore 64 becoming ubiquitous in homes and offices. As computers transitioned from being room-sized, expensive tools for experts to affordable, compact devices for the masses, the need for user-friendly interfaces became pressing. The field of HCI emerged to address this challenge, drawing on disciplines like computer science, cognitive science, and human factors engineering. By combining these expertise, researchers and designers could craft technology that was both powerful and accessible. Today, HCI plays a vital role in shaping the digital landscape, from smartphones and virtual reality to artificial intelligence and beyond. HCI's impact is evident in the seamless interfaces we use daily. It's the reason why you can effortlessly navigate your phone, reason why video games are immersive and engaging, and why online services are designed with your needs in mind. By putting humans at the forefront of technology design, HCI has transformed the way we live, work, and interact with the world around us. HCI is generally all about designing computers that understand humans and not the other way around. It's an interdisciplinary field that combines psychology, computer science, and design to create interfaces that are intuitive, learnable, and enjoyable. The goal is to make humans and computers collaborate seamlessly, like two old friends having a conversation. Isn't that just amazing? But here's the thing, not all humans are created equal. Some have disabilities like language barriers, cultural differences, which can make interacting with computers a real challenge. And boom, that's where computer accessibility comes in. It's all about designing technology that's usable by everyone, regardless of their abilities. And it's not just about people with disabilities. It's about making technology that is accessible to everyone. Period. Take voice-to-text software, for example. That's a total lifesaver for people who can't type or have trouble using a keyboard. And it's not just for people with disabilities. It's also super useful for anyone who is trying to write a text while driving, although I don't advise you to do that. Oh, I heard that. Stop talking in whispers. You asked about customizable font sizes, right? Although that's a big deal for people with visual impairments, it's also handy for anyone who's ever squinted at a tiny font on their phone. The point is, computer accessibility isn't just about checking a box or following some rules. It's about creating technology that is truly inclusive and empowering for everyone. So, what do you think? How can we make computer accessibility more of a priority? What are some ways we can design technology that is more inclusive and user-friendly? Making computer accessibility a priority is a no-brainer, right? I mean, who doesn't want technology that's usable by everyone, regardless of their abilities? But despite its importance, accessibility often takes a back seat in the design process. So, how can we change that? For starters, we need to involve people with disabilities in the design process from the get-go. It's called inclusive design, which of course is a total game changer. By bringing in diverse perspectives and experiences, we can create technology that is truly accessible and usable by everyone. Another key piece of the puzzle is accessibility standards and guidelines. I mean, think about it. If we don't have a shared understanding of what accessibility means, how can we possibly design technology that is accessible to everyone? That's where standards like the Web Content Accessibility Guidelines, WCAG, come in. They provide a roadmap for designers and developers to follow, ensuring that technology is accessible and usable by everyone. But even with the best standards and guidelines in place, accessibility can still fall by the wayside if designers and developers aren't properly trained. So, what can we do to change that? For starters, we can provide training and resources that teach designers and developers about accessibility and inclusive design. We can also encourage companies to prioritize accessibility and make it a core part of their design process. In expanding on this concept, let's discuss the designing tech that is inclusive and user-friendly. What does that even mean? In a layman's thought, it's just about having buttons and menus that make sense, but unfortunately, it goes way down more than that. It revolves around creating interfaces that are easy to navigate, with clear and concise language and minimal cognitive load. It means allowing users to customize font sizes, colors, and layouts to suit their needs and preferences. And it means providing multiple ways for users to interact with technology, such as voice, keyboard, and touch. But here's the thing with designing tech that's inclusive and user-friendly. It isn't just about checking a box or following a set of rules. It's about creating technology that is truly empowering and enabling for everyone. So, how can we do that? One way is to involve users with disabilities in the design process through participatory design. By working closely with users, we can create technology that meets their needs and is usable in real-life contexts. And, let's not skip the importance of continuous iteration and improvement. As we all know, technology is constantly evolving, and accessibility is no exception. So, how can we stay ahead of the curve and ensure that our technology remains accessible and usable by everyone? One way is to regularly update and refine our technology, incorporating user feedback and addressing emerging accessibility issues. By doing so, we can create technology that is truly inclusive and empowering for everyone. Design principles for accessible computing include perceivability, which is the act of making content accessible to all senses. Also, we've got operability, which is the act of making interfaces usable by all. And lastly, robustness, which is the act of making content compatible with different technologies. As we explore the world of accessible computing, we're working towards a common goal, creating a digital world that is inclusive, equitable, and usable by all. To achieve this, we need to understand the foundation of modern computing, the operating system. It is the backbone of modern computing, managing hardware resources, providing a platform for running applications, and controlling the flow of data. In essence, an operating system is the bridge between computer hardware and user applications, making it an essential component of accessible computing. But that's a pretty simplified definition. I mean, think about it. An OS is responsible for managing everything from memory and storage to input, output devices, and networking. It's just like the ultimate multitasker. Now, let's shift gears to process management. This is where the operating system really shows off its multitasking skills. It is responsible for managing multiple processes or programs that are running simultaneously. This involves allocating resources like CPU time, memory, and I/O devices. Process scheduling is a critical component of process management. The OS uses scheduling algorithms to determine which processes should be executed and in what order. But what are the different types of scheduling algorithms and how do they impact system performance? Well, scheduling algorithms are the unsung heroes of operating systems, working behind the scenes to optimize system performance. There are several types of scheduling algorithms, each with its strengths and weaknesses. First, we have the first come, first served, or FCFS scheduling, which is exactly what it sounds like. Processes are executed in the order they arrive, with no prioritization. While the FCFS group is quite simple to implement, it can lead to poor system performance if a long-running process blocks other processes from executing. Next up is shortest job first, that is SJF scheduling, which prioritizes processes based on their execution time. The process with the shortest execution time is executed first. SJF can improve system performance by minimizing wait times, but it can be challenging to implement in practice. We've got priority scheduling, which gives VIP treatment to processes that need immediate attention. The most important processes get to jump to the front of the line, but this can lead to starvation for lower priority processes. And if they're stuck waiting forever, they might just give up. Next up, we have round robin, that is RR scheduling, which is all about fairness and responsiveness. Each process gets a fixed time slice, called a time quantum, to run, and then it's the next process's turn. This approach ensures that every process gets a chance to run, but it can also lead to context switching overhead. Finally, we have the multi-level feedback queue, MFQ scheduling, which is a scheduling ninja. It combines the benefits of priority scheduling and round-robin scheduling, using multiple queues with different priority levels. Processes can move between queues based on their behavior, ensuring that each process gets the attention it needs. And if you're asking, which scheduling algorithm is the winner, then I just have to confess that it all depends on the system requirements and constraints. But one thing's for sure, each algorithm has its quirks and challenges. Before we go, let's not forget the referee who keeps everything running smoothly when multiple processes want to access shared resources. Take a wild guess. Let's see if you know him. Nah, it's none of those. This dude is calmer and easy to approach. It is synchronization. Synchronization is one of the unsung heroes of concurrent programming. It ensures that multiple processes access shared resources safely and efficiently, preventing conflicts, data corruption, and other nasty issues. But how does synchronization work, its magic? Well, it uses various techniques like locks, semaphores, monitors, and message queues to control access to shared resources. These techniques act like traffic lights, directing processes to wait or proceed, ensuring that only one process can access a shared resource at a time. For example, consider a bank that stores the account balance of each customer in the same database. Now, suppose you initially have X dollars in your account. Now, you take out some amount of money from your bank account, and at the same time, some random dude somewhere else is trying to look at the amount of money stored in your account. As you are taking out some money from your account, after the transaction, the total balance left will be lower than X. But the transaction takes time, and hence the person reads X as your account balance, which leads to inconsistent data. If in some way we could make sure that only one process occurs at a time, we could ensure consistent data. But once we've got our processes playing nicely together, we need to make sure they've got a place to call home, right? Oh, yep. That's where we shift gears into the world of memory management. It is the ultimate landlord, responsible for allocating memory to running programs and evicting them when they're no longer needed. But have you ever wondered how it decides who gets the penthouse suite and who's stuck in the basement? The answer lies in the memory manager's ability to assess the needs of each process and allocate the right amount of memory to keep them running smoothly. This, of course, requires a delicate balancing act, fitting together different memory requests without leaving gaps or overlaps. When a process tries to access memory outside its allocated space, the memory manager intervenes, denying access to the unauthorized area. This approach prevents processes from crashing the system and causing chaos. The memory manager acts as a digital bouncer, keeping the system safe and secure. Memory fragmentation poses another challenge. As processes come and go, they leave behind fragments of memory too small to be useful. The memory manager must constantly rearrange the memory landscape to optimize memory usage and prevent waste. Let's just see it like you're the manager of a busy restaurant. You have many customers coming in and out, and each one needs a table to dine at, but your restaurant has a limited number of tables, just like a computer has a limited amount of memory. As the manager, you need to decide which customers get a table and when. You also need to make sure that each customer has enough space to enjoy their meal. This is basically what memory management does. It ensures that each process gets the memory it needs to run smoothly without overcrowding the system. Now, let's talk about how memory management works. When a customer arrives at your restaurant, you need to allocate a table to them. In the same way, when a process starts running on a computer, the operating system allocates memory to it. But what happens when a customer leaves the restaurant? You need to free up the table so that another customer can use it. Similarly, when a process finishes running on a computer, the operating system needs to deallocate the memory so that it can be used by another process. So, with that, it's a wrap for computer science today. Thanks for staying with us to the end of this video. Don't forget to support our works by hitting the thumb button and sharing this video to all across the globe. You can also consider subscribing to our channel if you're yet to. We're glad. It's been such a fun ride with you. See you in our next video, which promises to get even more interesting.